Alright, so standard deviation, again, we're just going to use the calculator. If it's from a sample, we use S of x. If it's from a population, we use sigma x. The way standard deviation works is that the larger the standard deviation, the more spread out the data are, and the smaller the standard deviation, the less spread out the data are. And we're going to see this visually here in just a second. One last little bit, let me show you about standard deviation. The formula booklet has the formula for population and for sample. We don't need to do either of these by hand. You might just want to make yourself a note to use the calculator. So you can do them by hand, but I don't recommend it. I would just say use the calculator. Also, you have the variance formulas there. I don't really cover variance in the course. That's more for higher levels of statistics that we don't get into. So just a quick note on variance. Variance is the square of the standard deviation. So it's the number before you square root. So if the calculator has already square rooted it for you, so if you already have the standard deviations from the calculator, for population you just square sigma, and for sample you just square the S. Again, we don't really cover that in the course. There might be a homework question where it wants the variance, so you have to get the standard deviation first and then just square it. Alright. So the reason standard deviation is so important is for something called the empirical rule. This is very important, a very big deal in the course. It's the empirical rule. And you'll see right below variance, back on your formula sheet, is the empirical rule. So very important to understand and be able to use the empirical rule. Alright, so I think we're good there. So if the data are bell-shaped based on the histogram, so if we look at the histogram and we see that the data are bell-shaped, which is kind of that bell kind of shape, so based on the histogram, you can use the mean and the standard deviation to create a symmetrical bell curve. Remember, symmetrical means the same on both sides. It's like a mirror reflection on both sides. So in your homework, you should see the words bell-shaped in the problem. And if it's bell-shaped, you can kind of draw this little bell picture. So we're going to use some easy numbers for an example. Let's say test average is 70 and the standard deviation is 10. The way these numbers fit on the bell curve is the mean goes in the middle, 70, and you kind of draw a line about halfway down the curve, almost all the way down the curve, and then all the way down the curve on both sides. Kind of halfway down the curve, most of the way down the curve, and all the way down the curve. And in each one of those marks, you're going to add one standard deviation. So if the mean is 70 and the standard deviation is 10, that first mark is going to be 80. Then you're going to add another standard deviation, so that's 2. So 90, and then you're going to add another standard deviation, so 3, which is 100. So you're going to count by the standard deviation. So we can count by 10 because our standard deviation is 10. If our standard deviation was 15, we'd count by 15. We're going to do the same thing in the other direction, except we're going to go back a standard deviation to 60. We're going to go back again to 50. And back one more time to 40. So the structure is the same no matter what kind of data you have. If it says bell-shaped, whatever the mean is, you put it in the middle, and whatever the standard deviation is, you count up 1, 2, 3, and back 1, 2, 3. And that fills out what we call the bell curve. Each one of those values is at that mark. It's at the mark on the curve. Remember, the curve represents the frequency of each value. So each one of these little areas is like a bar representing the frequency of how many numbers occur in that. So remember, this part is actually relative frequency. So remember, this is a smoothed over histogram. These are actually bars of certain heights. So the higher frequency are the taller parts of the curve, and the lower it goes, the lower the frequency. So that most of the data is in the middle, and less data trail off on both directions. So we've come up with something, and I say we, statisticians have come up with what's called the empirical rule. And what that tells us is that over time, the more the bell-shaped data they've studied, they've noticed some patterns and some trends. And so the patterns they've noticed are the numbers on your chart. They noticed that for bell-shaped data, approximately 68% of the data lie within one standard deviation. And these are estimates, but they're pretty good estimates. Over time, they've gathered this data. So if your data is bell-shaped, 68% of your data fall within one standard deviation. And again, that's the majority of your data. And they also noticed, again, given that you have bell-shaped data, over time they noticed that approximately 95% of the data lie within two standard deviations. So between this mark and this mark, they saw that about 95%, including the middle 68, and then these little parts as well, comprise about 95% of all the data. And the last thing that they measured is that 99.7% of the data lie within three standard deviations. So 99.7% lie all the way here and here. Notice there's a little tiny bit beyond 3, not much, but a little bit. The entire curve represents 100% of the data. So just like on relative frequencies add to 100%, this curve's area, all this space, all together is 100%. So given that the curve is symmetrical, if 68% lie within one standard deviation, that means that 34% lie in this little area here, and 34% are here. We can also figure out that if the area here is 95% and 68 of it is taken up in the middle, if we subtract 95 minus 68, that leaves us 27% between those two sides. And if I divide that evenly, since everything's symmetrical, that tells us that 13.5% of the data lie between 1 and 2 standard deviations above the mean, and 13.5% of the data lie between 1 and 2 standard deviations below the mean. So again, everything is symmetrical. Continuing this trend between 99.7 and 95, if I subtract those two values, that's where 4.7% of the data are. So if I split that in half, then 2.35% of the data are between 2 and 3 standard deviations below the mean. And everything's symmetrical, 2.35% of the data are between 2 and 3 standard deviations above the mean. And then that leaves a teeny tiny bit for those outer tails. So we know the whole curve is 100%. We've covered 99.7 of it. That leaves a tiny bit, 0.3, left in those little tails. If we divide that by 2, it's a very small percentage. So 0.15% beyond 3 here, and 0.15% beyond 3 here. And if you add all of these numbers together, you should get 100%. So there's lots of questions that we can ask based on the empirical rule. Now, knowing these 3 values, we can break the curve up into all these little sections. So what we're going to do is we're going to practice using the empirical rule with this same scenario that we were talking about earlier, a test average of 70, with a standard deviation of 10. So let's kind of see how that all gets put together. So at the top of page 7, it says, from the example from the previous page, use the empirical rule to answer the following questions. Approximately what percent of students made an 80 or better on the exam? So 80 was 1 standard deviation above the mean, or better means all the way up to the top of the curve. So if we look at our reference here, 1 standard deviation's here, all the way up to the top of the curve. So we're going to add this percentage, and that percentage together. And I believe you get 16%. So this part of the curve from 80, which was 1 standard deviation, to the top is 16% of the data. In this case, we're talking about student averages. So about 16% of the students got an 80 or better. The next question says approximately what percent of students made below a 60? So now we're looking at, oops, sorry, you can't see it. Now you're looking at below a 60. So if we come back over here, 60 is 1 standard deviation below the mean. We're looking below a 60. So that's this side of the curve. Notice that it represents the same tail as the top, and since everything's symmetrical, it's going to be the same answer, 16% of students. So everything's very symmetrical on a bell curve. And the last question, approximately what percent of students made between a 60 and a 90 on the exam? So 60 is here, 90 is at 2 standard deviations. So we're looking here to there. So we're going to add this 34, that 34, and that 13.5. I got 81.5% of students. You're going to have a lot of empirical rule questions on your homework. You want to draw out your bell curve nice and spaced out. You want to label it with the mean and standard deviation they gave you, and then use the empirical rule percentages to answer the question. Now you can memorize all these little pieces, or remember these 3 numbers are given to you on your formula sheet, and all you have to do is use those 3 numbers, and you can figure all of these out without having to memorize them. So that's up to you, but you do need to know how to use the empirical rule, and then it only works for bell-shaped data. So it has to be bell-shaped. It has to say the words bell-shaped somewhere in the problem. All right, so just emphasizing that one more time. We can only use this rule if the data are approximately bell-shaped. So you have to look for those key words when you're working these problems, bell-shaped. All right, the next type of calculation we're going to learn is called Chebyshev's inequality. So in most cases, data are not bell-shaped. And I say most. There's a lot of times when it's not bell-shaped. Usually they're skewed right or they're skewed left. So for data that are skewed or the shape is unknown, which means it's not stated in the problem, we use what's called Chebyshev's inequality. So this is a more general rule that we can follow when we don't have that nice, pretty bell-shaped. So for any data set or distribution, at least, and this is the formula, 1 minus 1 over k squared times 100% of the observations lie within k standard deviations of the mean. K is any number greater than 1. So this formula, 1 minus 1 over k squared times 100%, that will be given to you on the exam. I don't know why it's not on your formula booklet, but I'm going to print it for you separate that you can have it when you take your exams. So let's look at an example of how to use Chebyshev's inequality. So it says if we want to know the percent of data that are within 2 standard deviations, then that means k equals 2, and the homework will say it just like that. So what you're going to do is do 1 minus 1 over, you're going to plug in k right here, there's k, which is 2 squared, and then multiply by 100. When you put this in the calculator, make sure to use the parentheses just like that. 1 minus 1 over 2 squared times 100. And if you just type that in, it will give you 75. And it's a percentage, so 75% of the data would be within 2 standard deviations. Now remember, when it's a bell curve, you use the empirical rule. So within 2 would be 95%. When it's not bell-shaped, when we don't know what the shape is, only 75% of the data would be within 2. So Chebyshev inequality is more general because we don't know the shape. So let's do that one more time. Approximately what percent of the data are within 1.5 standard deviations of the mean? So we're going to do 1 minus 1 over 1.5 squared. And we'll multiply that by 100. So you can type it in just like that with parentheses. 1 minus 1 over 1.5 squared times 100. It will follow the order of operations. It will square, it will divide, it will subtract, and then it will multiply by 100. So for this one I got 55.5 repeating. And the homework will tell you how to round, so I'm going to say 55.56%. So you'll have to round, but you'll just have to see what the homework specifies to round. I just noticed the microphone was covered up. Hopefully you guys could hear all of that. So you just plug in your numbers. You plug them right into the calculator. Make sure to use parentheses. It will follow the order of operations and give you the correct answer. And then you round just based on how the homework problem or test problem specifies the rounding. Alright, I'm going to stop there. That finishes 3.2, and I'll start a new video for section 3.4.